All right. So as you know, we always do a check-in with technology. And look at this. Siri, this huge, hot, awesome new iPhone app that lets you talk and the Apple servers respond to something. Look at this. They now have Evie. Evie is this, remember, Siri is only on the iPhone. In fact, it's not even on the iPhone 4, it's only on the iPhone 4S. So they came up with Evie. And Evie is this now competitor, 99 cents, and it's on all platforms, iOS and Android, which is awesome because the competitor to Siri initially was Iris, and that was only on the Android. And now we have something that works on both. And actually, I tried it, and it works. What is the time difference between here and Chicago? 2 hours. I don't know if Siri could do that. I said, what is the ORD? Yay. What is the ORD airport code? Oh, that's Chicago, I think. But it was really cool, and I tested it. It was awesome. All right, so that's the news for the day, and then we'll pause for a second and then get some mics. Today we're going to be learning about functions, and functions are really at the at the base level that every piece of software that you ever use has at its root, honestly. It's wonderful. This is a review. You saw this last time. This is a function machine that you turn, like a sine. You put an input. We saw this when we were talking about abstraction. And x is the input. You turn the sine crank, and whatever the input is, you compute the sine of that input. Hopefully it's an angle, and out comes the result. Okay? So that's a basic function. You've seen that before, and this is a nice function diagram from Simply Scheme, Brian Harvey's book. So the basics of a function are very simple, but they're really important that you understand them. A function is something that takes 0 or more inputs. So it can take any number of inputs. And in this metaphor, you see the metaphor, we have the inputs in this diagram are kind of the tubes of the information flowing into the top. The same input must yield the same output. So that's a really critical, important decision, because what that says is that the output is a function only of the input. It's not a function of prior state, what happened yesterday or a moment ago. You can't set some state and have it affect that function. That function cannot be affected by state. And there's no variables being changed at all. And there's no side effects. In the purity of functions, you have nothing else happen other than things come in. Could be numbers, could be words, could be sentences, could be data structures, massive data structures. And then something gets calculated, and there might be an output, or there might not. It says here returns exactly one output. So the idea is that the pure function always returns one thing. But what if you want to return two things, like your age and your height or something, right? Put in a person and you get the age and the height. You'd have to wrap that in a data structure so that could be one thing. You have to kind of wrap it like in a package. You couldn't just do two things, okay? So the important thing on this slide is that nothing else can affect the function. Prior state or mutation in the function should do nothing else, like make a robot. How about here, Dan, let's make a function in which I make a robot walk across the street. Well, no, that's a side effect, and that's not what a function can do. That's a command, not a function, okay? So that's what the idea. And the metaphor is this little guy comes out of here. If you pass in, here's a subtraction, and you see a 4 comes out of 5 minus 1. So here is a description. As we move forward, we're talking about functions. One of the really important things in a function, this is now in math, I'm reviewing math class for you, is domain and range. Again, this is all something you should have seen before. So domain and range, really, I think of it as D and R, like doctor. Okay, so domain is the input, the class of inputs that your function can take, and the range is the class of the output. So it's DR, think of doctor, okay? So here's some examples of domains and ranges. Here's some domains. What's the domain of square root of? What is the set of inputs that works for successfully? Does it work for the letter hello? No, square root of, what does square root of hello mean? It doesn't make any sense. Positive numbers. And if you had a more expressive square root, you might even have a square root that could produce complex numbers, in which case you could expand that to all kinds of numbers. But for us, we can only hand positive numbers, which is larger than saying positive integers. Like I can pass it square root of 4.5. That can actually work. Okay? Length of takes a sentence. We'll talk about what a sentence is, a word and number in a moment. It takes a sentence, computes the number of letters in that, a word without spaces, or just a number. Less than has to be What's cool about less than is you can compute it on numbers. Obviously, it's 3 less than 4 true. You can also do it on words. It says, is hello less than happy? And no, in the dictionary, hello happens after happy, so that's false. Isn't that cool? Very powerful that that less than function works on words as well. It's more expressive in that sense. And works on Booleans, which are true and false. That's all that is. And it returns true only when both of them are true. And letter blank of blank has 2 different types. Letter blank, which is a number, has to be a unique number from 1 to the input length of the second input, which is a sentence, a word, or a number. So that's examples of domains, okay? Ranges are the outputs. What's the output of square root of? Well, it says non-negative numbers. Okay? Length of has the input of, it could be a sentence of words. It could be CS10 is great, and length of calculates something and returns something of a different type, which is a number, which might be 12, or how many characters were in that sentence. Less than also returns a Boolean, true or false, and returns a Boolean, and letter blank of blank returns a letter. So now you might be asking, what are all these what's the family of types? And this is a new slide from this semester because I realized as we're talking about types, you should know at least a couple examples of them. So we start at the smallest, innermost level. Because these are kind of nested eggshells, like egg of an egg, like the Matryoshka dolls. They're kind of packed inside. Digit is the simplest thing I could think of. Just 0 to 9, that's all you're allowed to have. That's a digit. If I say, oh, the input takes, this function's domain is a digit, it better be only 0 to 9, that's it. A character is a little bit more general than that, right? You see, it's a little bit larger because it includes alphabetic letters as well as the digits as well themselves. And I would say character counts like pound sign as a character. So it's not just letter A to Z, but it's also the things on top of the numbers on the typewriter, the characters. A word means more than just a single length 1. It means any set of characters. That's a word, but without spaces. And sentences is a set of words with spaces. It can also have no spaces. So a sentence of hello, that's a valid sentence, right? It doesn't have to have punctuation. I mean, in English, you have to have punctuation and capitalization. We don't care about that here. You get that? So that's kind of a nested set of types. So as we're talking about domain and range, especially on the Quest, you might see, nobody laughed. That usually gets a laugh. So on the Quest, I might be asking you for this kind of a thing. So that's the kind of thing you should kind of be fluent about. I might ask you, here's a picture. How about another kind of type? How would that fit into this? Like how about, I don't know, negative numbers. Would that be in here? Where's numbers in general? Numbers aren't digits. They're bigger than digits, but they don't allow for characters. So you have kind of this Venn diagram thing going on where you might draw a little picture where numbers intersect with this big picture of that concentric circles. Okay? So why functions are great. And that disappeared, and it's going to appear again. Functions are great for the following reason. We're going to see later in this semester, later in this course, that you're going to have the power. We're going to teach you how to program data centers. Like, what do you mean? You mean the things that Microsoft and Google and Amazon, they have like a massive factory with 1 billion machines in there? Uh-huh. You mean we're going to learn the techniques that they use to program those things? Uh-huh. And the cool thing about it is if you live in a functional world, if you live in a world in which there's no mutation, there's no state changing where you're assigning variables, you're just building things out of these functions. Here's a big pipe set up where inputs come in and the pipes, and maybe subpipes and subpipes, and there's one output here. If you can write a program in that functional style, we'll talk about programming paradigms next time, then that kind of a program can be massively parallelized. You're like, what does that mean? It means if I have 10 of these things, I can put all 10 of them on 10 different machines, and if the inputs are fixed, it should just work in that machine. The machine shouldn't need any more information than what the input is, which is really powerful. It means I can package up a computation as, here's the function, here's the inputs going to fit into the top holes, pass it over to somebody else, and that will get computed, and the value can come back to me. And you can think about how you'd parallelize. If you can think about some massive computation that can be built on functions, I could pass it to 10 million machines, and they all compute something, they come back, and there's my answer. And I might have to keep passing it as I take those 10 million result values and then work my way down to one answer, but that's really powerful. So we somehow the data center picture got messed up, but the data center model of how you program, if you live in this functional programming paradigm, again, we'll see that next time, you can massively parallelize those computations. And that's really, really cool. So one of the things you've seen in lab and hopefully at home and played with and really enjoyed is the Scratch programming language. And we think Scratch is outstanding. We really do. We love Scratch. We think it is an amazingly great starting point. But it had some limitations. It didn't have generic lists where I could make a list on the fly and pass it back. It didn't have functions at all, really. The new version of Scratch, hopefully, will have some functions, but a limited kind. They're going to be commands, not functions. We'll talk about that in the next slide. So we, Berkeley, and some folks in Germany, built the new version of Scratch. We call it BYOB, or Build Your Own Blocks. Doesn't stand what you think it stands for. It's going to be called Snap, and that's going to be really cool. And in fact, I had a version running in the browser. So let me now show you the demo of Snap running in the browser. Wow. This changes everything. You can program this without downloading anything. If you walked into like an internet cafe where you couldn't download anything, it was all locked out, you could still do programming. If you had that itch that you had to scratch, like, I got to program something right now, you could just work in a browser and do this. Also, you could take, say, an iPad, and you could just sit with an iPad and with your finger just be dragging blocks, just touching and dragging the blocks and programming. Wonderful. So we're really excited about the potential for Snap, and we're going to release it pretty soon. So let's talk about why you use functions. So here's an example of 3 blocks, and they're completely different, right? Just like my 3 different recipes I had on 3 different pages to make a strawberry milkshake, a cherry milkshake, and a raspberry milkshake. Remember how that wasn't really 3 different pages? We learned something about that? Look at those 3 different blocks I wrote. Pen down, repeat 4, move 25 steps, turn 90 degrees. That was a square of size 25 edge. And the next one, same exact thing, except move 100 steps. The last one, same exact thing, except move 396 steps. You're saying to yourself, in the same way you were saying to yourself with the milkshake analogy, wait, Dan, why write this down 3 times? Just say insert fruit here, and you've got a fruit milkshake. I now hand you exactly the analogy of what we do in computer science. This is the generalization we talked about in the first lecture, which was thinking about an input now. And that input might be length. And as I go through, rather than saying move 25 or 100 or 396, that's all the common piece, I move length steps. And now I have a generic draw square. Isn't that great? Should I stop there? Should I stop with draw square? Can you see a way to even be more abstract? Think like a computer scientist. What about here do you see as a hard-coded number? 4 and a 90. That's a square. Can anybody think about an exciting space where we could generalize that? And I'll ask that as a hypothetical. You're right, person at home, because repeat 4, turn 90 is for a square. I've hard-coded a square in there. How about a triangle? Those numbers change. But the rest of it's exactly the same, right? It's repeat 3 and then turn 120, right? So now you're saying to yourself, this could be even more generalized. This could be even more powerful and more useful for other folks. Rather than draw square, I have draw regular polygon. Isn't that beautiful? So I could have 2 arguments, length and number of sides, and do some repeat number of sides and do some calculation of 360 over those number of sides for the angle turning. Isn't that cool? So that's a way to think like a computer scientist. That's a way to think abstractly. That's why functions are cool. Without functions, which is what other languages without functions have, you can't do that. You have to write those 3 examples for those 3 sides. You have to write a script that does a triangle, and a script that does a square, and a script that does a pentagon, and a script that does a octagon. And you're saying to yourself, why can't I generalize this? And without, it's tying your hands behind your back if you can't generalize this in a wonderful computer science way. And that's what we do in computer science. So you're taking steps, baby steps to being a full-fledged computer scientist. It's awesome. Feels really good, right? Thinking about this stuff? Woohoo! Okay, so why do we use functions? So one of the things you can do with functions is you can cascade them into each other. So here's an expression at the bottom. Join. I am with join. My age minus your age, years older than you. What does that look like? Well, I start with, if I think about it from kind of the smallest part, the innermost part, people often think of this, and I recommend this myself, looking at the innermost part of a computation and working your way out. So join my age minus, so first of all, the innermost one is my age minus your age. That's their difference, okay? That's a minus block, which has two inputs. My age and your age are here as the inputs, and out comes this difference, okay? That's being fed into what? Another join block, or a join block, it's the first one. A join block that says, take that number and put that in number, and hopefully, ooh, here we go, we're connecting now with domain and range. Hopefully, the range of subtraction is a subset of the domain of join. I'm going to pause for effect here. You see this? Because I'm plugging them into each other. It's like I can't just take this microphone and say, oh, what happens if you plug it into the wall socket? It doesn't work. The interface doesn't work. But functions the same way. I have to, for this to work, it has to be the case that the output of the subtraction produced a value that was meaningful to the input of the function using it. And that function using it is join. Does it make sense? Can join handle numbers? The answer is yes. It takes whatever it is and smushes them together into one big thing. So it does. So we're happy. And it puts that together, and it smushes that together with the phrase, years older than you, and blank, now you've got a sentence, 7 years older than you, okay? And then the output of that join is another sentence. That's the input to the last join, which takes an I am and there. Can join take a sentence? Thankfully it can, and so that expression works. So the idea, this is called functional composition. We're composing functions like this. This is an expression. It looks very beautiful and graphical. Before the world of BYOB, you had to see this in text. This had to be how you coded, by typing. This is now dragging blocks, and it makes sense. And the wonder of BYOB and other languages like it that support this is that it knows a little bit about types. It knows a little bit about sentences and words and booleans and things. And so there are times when you want to drag something and it won't fall into the hole of the function input. You drag it, boop, it won't why can't I drag it there? Because it doesn't make sense, because the system knows that the output of this block doesn't make sense as an input to the other block. So it won't even let you drop it. Isn't that cool? So it makes it more kind of child-proof in that sense. Isn't that great? Buggy program-proof, I'll say. Okay, that's really the better way to do it. So these functions are the building blocks of everything we're going to see. From this point on, from this lecture on, it is all about functions and building massively awesome, towers of knowledge based on functional methodologies, functional paradigm programming. Okay? The idea of taking a problem and breaking it into functions is called functional decomposition. Okay? So, types of blocks. And this is something that I had my staff want to remind me about the difference here. The bottom two are the functions. Okay? They're not always green. They can be other things that return values. Join hello world, you've seen before, that's a reporter. We call that a reporter. And when I say we, BYOB calls that. So BYOB calls that a reporter. If I say function or reporter, they're the same thing in this context. Okay? Predicate is exactly like a reporter. It's a special case of reporters that returns a Boolean. So it's just a special case of that. Don't get confused by a predicate. It's just like a reporter, just happens to have a special thing about this kind of six-sided polygons which returns a true or false. But it's also a reporter. A command is the top guy. A command is not a function. It is a do something block. It is exactly the purpose of a side effect. For example, move 10 steps, and all of a sudden your sprite goes blink, or play a sound, or make the robot do something, or draw a picture, or change some state. Those are all command blocks, and notice they're not shaped like round edge things. They have this kind of jigsaw puzzle things. Everything jigsaw puzzle based is not a function. Everything that's not, which is round edged or kind of square, kind of six-sided things with the kind of angly guys, those are functions, okay? So I'm going to give you a quick preview. I'm going to show you some functions. We'll look at that, some code now. We'll do a little demo. And I'm going to give you a little taste of a preview. You guys want a taste, or should I save it to the end? This is now a chance where you get some input. Do you want me to give you a little taste of possibly the coolest thing of functions now, or should I just wait and we'll see it in a couple of weeks? Because I don't want to, I mean, if I'm going to confuse you, I'll choose not to confuse you. But I can give you a taste, a free sample. First one's always free. You know, that's what my drug dealer tells me. So anyway, the point is, I joke, you know, aspirin. Right, so here we go. So we're doing recursion, and we're going to do a little bit of function stuff. So let's go in and boot BYOB. So here's an example. Let me just give you an example. Here's an example of composition. Letter, length of this, of hello world. Length of returns a number that passes to letter blank of hello world. What's the length of this? 5. What's the fifth letter of hello world? O. And double click this guy. Oops, double click this guy, and O is the result. So that's the example of the composition we saw before. Okay? This is an example of, and here's how you edit things. This is an example of being very general with that draw regular polygon. Remember we talked about not draw square, but the abstraction of that into a function that can handle both the number of sides and a size. This is repeat n, where n is the number of sides. You want to be really good about thinking about your names for these, okay? So n is a generic number. Maybe I should have said sides there, actually. That would have been even more useful in terms of a name. And move size steps. That should be maybe the edge size. So do this, and here's 360 over n, pen down, pen up. And as I say here, that's fine. And I can now do this, and now I can move my character over here. I can now say looks, actually it's pen, and say clear. And now I can draw this, 10-sided, and there's my 10-sided character. Generalized, right? This was a square, but now it's general. Isn't that really powerful stuff? And now you might say, ooh, let's make it more general. Let's make it general by adding the input with the pen color this, with the thickness of the pen that. You can imagine adding more things that will affect that drawing and make it even more general, right? Because this is now assuming, notice, by the way, the shape of this. What's the shape? Is that a function? No, because it's a it's a command, and thus it's not a roundy guy, and because its job is to do some output, some side effects, which is to draw and affect the paint window, affect the stage. Okay? Here's my pick random 1 to 10 to prove this is not a function. 1 and 10 aren't going to change. Nothing on my sleeves. Not changing 1 to 10. And 3, okay. And then one more time, and 9. So there, immediately not function. Okay? And countdown. I am now going to blow your mind. I want to show you how something can count down from 10 to 1 and say blast off. Okay? So let's see this. Say countdown 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. How did it do that? Let's define countdown. Okay? So how would we think about how to build a function to do a countdown? Okay, it passes in a number, 10. Domain is a number, and then it's going to produce a sentence, which is that number and all of that. Okay? How will we produce that? So let me see. I'm just going to let you stare at this. And let's see if we can process this together. I think this is so powerful and so beautiful. We have an if statement. An if says is like a decision point, right? If this, go that way, otherwise go this way. If the test is true, you do the first thing. Otherwise, you do the second thing, okay? So let's do the easy case. If you pass in 0, I want to return blast off. So I report blast off, okay? Because I'm a reporter. And this is a function, right? It's just a rounded guy, okay? Not a kind of puzzle piece guy. So if n is 0, return blast off. That's called the base case. That's easy. If it's not 0, then what if I had a helper called blast off who could calculate one smaller than me? Let's just say I had that, okay? Let's call it blast off helper, okay? So I have blast off helper that can produce the sentence 987654321 blast off, okay? And they're going to produce that as a sentence. How would I take my 10 and work with what the return value of the helper is to do 10 987654321? Get that? So how would you do that? I have a helper. returning 9 through 1 blast off. 9 through 0, I guess, blast off, right? How could I take my 10 and work with what my helper does to actually return 10 to 1 blast off? Let's think about that. I could join them. If I joined my 10 with my helper, then that would produce the answer. My helper is reporter, the guy 9 through 1. Helper. Well, it turns out my helper, this is the biggest idea that I'm kind of leaking today, so it's not going to be as big as a bang when we talk about it in a couple of weeks. My helper, who's my helper? It's me. If I can handle that, if I can handle and successfully produce 9 through 1, how do I take myself's answer, 9 to 1, and add it to what I've been given, the 10, to produce 10 to 1? I just join them together. So watch. I join 10 to, I join a space to, I call myself recursively. This is going to blow you. I mean, there should be no understanding in the room right now. And I'm glad there isn't, because it's quiet, and that's what you get when you have no understanding. It's fine. I'm never going to test you on this. It's just a little taste. Just a taste. Not a, right? You will eventually be taken much more slowly as you walk very slowly. But the idea is, I wrote a function in which I am part of the solution. You're going to have to, there's this phrase, a king is the son of a king. But wait, how's that? Then who's the chicken? Who's the first king if the king's the son of the, how did there be, right? Right? It's kind of the same mind-blowing kind of idea of how did it start? Fortunately, we have how it started, which is really how it ends, which is we have an ending point here, right? If we didn't have, if I just had, this is good. If I didn't have the if and just said count on n, report, join n, count on n minus 1, I would go on how long? Forever. Because I'd keep looking for who's the first king in the same kind of thing, right? I'd be looking for the first king. So this is one of the really brilliant and beautiful ideas in computer science. But again, okay to have total cluelessness about that now. Just kind of get the idea that you can actually write a function for which the function you're writing is part of the solution. It's just this really wonderful kind of Escher diagram of hands writing hands diagram. Okay. So here's the summary. Here's the big idea of what functional programming is. Computation in a functional programming paradigm model is that everything is as simple as that black box. That black box F has some number of inputs, maybe none, and has one output. And nothing else affects that computation. Only the input values. Nothing else. And that's brilliant and beautiful and powerful. The idea of taking a big problem, oh my gosh, how do I write a web server? That would be really big, right? I have to handle requests and do the thing and store in a database. Complicated things, words you probably don't even know what they mean. It's okay, we'll teach you most of those words. Discussion, by the way, is a great time for you to ask questions of, Dan said this word database. What does that mean? And your TA will then take a chance and describe what a database is as well as they can. If you can't Google the answer, by the way. So here's a function. F takes an input x. What's really happening, here's a computation. X plus 3 times square root of x. What's really happening is inside that, abstractly, inside that is itself more small functions. It doesn't happen to have f inside, so it's not using recursion. It has a plus and a square root. And it's taking the x, and by the way, taking the result of those two guys, the plus and the square root, and passing it to the output. And it's taking the x, and it's passing it to its two inputs, here and here. And so those inputs get passed to the inner piece of it, which is how you're feeding the inner functions inside to produce the result. The key idea in this week is you need BYOB, not Scratch. So if you were playing with Scratch all along, you got to stop now that we're entering the function world. You're now entering the function world. And so from now on, you'll be returning values, exploring that, and practicing functional decomposition, which is taking a big problem and breaking it down to small ones. Thanks so much, folks. We'll talk about different programming paradigms on next lecture.